Dear students, so in this class, let us discuss about conjugates and discriminants. I thought that all of these things are familiar with you. These things are studied in algebra, abstract algebra. So, what is a conjugate? If k equals q theta be a number field. So, first we consider if k equals q theta be a number field, then there are distinct monomorphisms sigma from k to c. Sigma be a k equals q theta, c be the complex number field. Then we define the number of monomorphisms from where to where, k to c. For example, if k equals q of I, then you define the first monomorphism, sigma I1 from, so sigma 1 of x plus iy, sigma 1 from k to c. That is sigma 1 of x plus iy equals x plus iy. That is one of the monomorphism. You can define another one, that is sigma 2 of x plus iy. Sigma 2 of x plus iy is x minus iy. This is another monomorphism. Define sigma 3 of x plus iy, that is minus x plus iy. Sigma 4 of x plus iy, and so on. So, if k equals q theta be a number field, then we can define number of monomorphisms from where to where, sigma from k to c. Okay. So, now let us consider a result. The theorem states that if k equals q theta be a number field of degree, its degree of degree n. K equals q theta be a number field of degree n over q. Degree n over q. Then there are exactly n different monomorphisms, that is sigma I. There exist exactly n different monomorphisms sigma I, where I equals 1, 2, etc. up to n, from where to where? From k to, so sigma I from k to c. Sigma I from k to c, where I ranges from 1 to n. Here the elements sigma I theta equals theta I are distinct zeros in C, complex field, of the minimum polynomial of theta over q. So the theorem states that if k equals q theta be a number field of degree n over q, then there exist exactly n distinct monomorphisms sigma I from k to ci, where I ranges from 1 to n, not to ci, sigma I from k to c. Sigma I from k to c, where I ranges from 1 to n, with the sigma of I theta equals theta I, are distinct zeros in C of the minimal polynomial theta over q. So how to prove this one? The proof is, let theta 1, theta 2, etc. theta n are distinct zeros of minimal polynomial p over q. Okay. So, minimal polynomial p over q. Theta 1, theta 2, etc. theta n are the distinct zeros of the minimal polynomial p over q, means p be a minimal polynomial for each theta I. Okay. If theta 1, theta 2, etc. theta n are distinct zeros of p over q, then immediately we can say that p be the minimal polynomial for each theta I. Hence, there exists an isomorphism. Sigma I from q theta to q of theta I, q of theta. Why? Because p be a minimal polynomial over q. Since P be a minimal polynomial over each theta I, then there exists a unique monomorphism sigma I from q of theta to q of theta I. It is defined as sigma I theta such that sigma I theta equals theta I. Sigma I theta equals theta I. Okay. So if alpha fall in q of theta, then this alpha can be rewritten as alpha equals some r theta. Okay. So what is r here? With a r fall in q of t means r is a rational polynomial. R fall in q of t with a degree of r strictly less than n. Okay. So since P be a minimal polynomial for each theta I, there exists a unique monomorphism sigma I from q of theta to q of theta I such that sigma I theta is theta I. Why this is so? Because P be a minimal polynomial for each theta I, also P be the minimal polynomial of theta. Okay. So if alpha fall in q of theta, then this alpha is written as some r theta, where r fall in q of t with a degree of r strictly less than n. And sigma I of alpha. So what is sigma I of theta? Sigma I of theta is theta I. So what is sigma I of alpha? Sigma I of alpha is sigma I of r theta. Okay. What is sigma I of theta? Theta I. So sigma I of r theta is r theta I. Sigma I of alpha equals sigma I of r theta. Again, sigma I of theta is theta I. Therefore, it is r theta I. Okay. So sigma I of alpha is, that means sigma I of alpha equals r theta I. That is, there exists exactly where I ranges from 1 to n. That means there exists exactly n distinct monomorphisms from where to where? Sigma I from k to c. Agreed. Now again, suppose that also we have to show that the elements sigma I theta equals theta I are distinct zeros in C of the minimal polynomial of theta over q. So conversely, suppose that sigma from k to c. So listen, let sigma from k to c be a monomorphisms. Then sigma from k to c be a monomorphism. That means sigma be an identity. Sigma is an identity. Okay. Sigma is identity on Q. Now we have 0 equals sigma of p theta. Why? Because that's a polynomial. Sigma of p theta. Okay. Sigma of I theta equals theta I. So what is alpha equals r theta, and sigma of theta I, sigma of I theta equals theta I. So 0 equals sigma of p theta. Sigma of p theta equals p of sigma theta. Okay, p of sigma theta. So means p of sigma theta equals 0. P of sigma theta equals 0 means sigma theta be a one of the, what is sigma theta? That means sigma theta be 0 of pa. But we already stated that let theta 1, theta 2, etc. theta n are the zeros of p, of the minimal polynomial p over q. But here we know that sigma theta be a 0 of p. That means this sigma theta is 1 of theta I. Why? Because here we obtained sigma theta is 0 of the minimal polynomial p over q. But we already assume that theta 1, theta 2, etc. theta n are the zeros of minimal polynomial over q. So we can combine. We have sigma theta is 1 of this theta I. Sigma theta is 1 of theta I means sigma is 1 of sigma I. Okay. Sigma is 1 of sigma I. So that is what we requires. Clear? Yes. Now Now we define the field polynomial. What is a field polynomial? How to define the field polynomial? The field polynomial over Q. So the field polynomial over Q or the field polynomial of alpha, the field polynomial of alpha, field polynomial, the field polynomial of alpha over k, k with the number of fields, is defined as f alpha t is defined as f alpha of t equals product I ranges from 1 to n t minus sigma I of alpha. Field polynomial of alpha over k is defined as, where k be a number of fields, f alpha of t equals product I ranges from 1 to n t minus sigma I of alpha, where alpha fall in q. Okay, what is q? Sorry, alpha fall in q of theta, or it is k. Alpha fall in k equals q theta. So f alpha t is product I ranges from 1 to n t minus sigma I of alpha. Now come to a theorem. The coefficients of the field polynomial are rational numbers. Now let us discuss what is the characteristic of, or what is the nature of the coefficients of this polynomial. So let's see. We see that the coefficients of the field polynomial are rational numbers. That means f alpha t presents in where? That means f alpha, we have to show that f alpha of t that presents in q of t. F alpha of t presents in q of t. That is what we are recursing. So here let us discuss the nature of the coefficients of this field polynomial. And the theorem says that the coefficients of the field polynomials are rational numbers. How to prove this one? So we have, its proof is, we have alpha. What is alpha? In previous theorem we defined as that alpha equals r theta. So what is r here? R equals q of t or k of t, whatever may be. R fall in k of t, number of fields, with the degree of r, strictly less than n. Okay. Now come to the field polynomial. By definition, the field polynomial f alpha of t equals product I ranges from 1 to n t minus sigma I of alpha. Okay, so that equals product I ranges from 1 to n t minus, what is sigma I of alpha? Sigma I of alpha is r theta I. From where? We already proved this one. Alpha equals r theta. Okay, so sigma I of theta equals theta I. Therefore, sigma I of alpha equals r theta I. Clear? By the previous theorem, we have sigma I of theta equals theta I. Therefore, sigma I of alpha equals sigma I of alpha equals sigma I of r theta. Why? Because alpha equals r theta, so it is r theta I, where r fall in q of t, or here it is k of t. Okay, so equals product I ranges from 1 to n t minus k equals q theta, so it is product I ranges from 1 to n t minus r of theta I. Where, what is theta I? We also know that theta 1, theta 2, etc. theta n means I ranges from 1 to n theta I, that are the zeros of the minimal polynomial. Theta I are the zeros of minimal polynomial p over q. Zeros of the minimal polynomial p over q means whose coefficients are in q. What is theta I? Theta I are the zeros of the minimal polynomial p over q. That means the coefficients of p are in q. Okay. Therefore, the coefficients of f alpha t. What is f alpha t? Is product I ranges from 1 to n t minus r theta I. theta I are the zeros of the minimal polynomial p over q. Therefore, whose coefficients are rational numbers. Now, therefore, the coefficients of f alpha t are of the form h of theta 1, theta 2, etc. theta n. Okay. Why? Because theta I be the zeros of the minimal polynomial p over q. Therefore, the coefficients of the field polynomial f alpha t is of the form h theta 1, theta 2, etc. theta n, where h of t1, etc. tn, where h of t1, etc. tn, h of t1, t2, etc. tn are symmetric polynomial by definition. They are symmetric polynomial in where? In q of t. Symmetric polynomial in q of t or q of ti means q of t1, t2, etc. tn. Hence, the coefficients are in q. Okay. We have alpha equals, let alpha equals r theta, where r fall in q of theta. Q of theta is k with a degree of r is less than n. But the field polynomial f alpha t is defined as in this way. Product I ranges from 1 to n, j minus sigma I of alpha. But we know alpha equals r theta as well as sigma I theta is theta I. So what is sigma I alpha? Sigma I of r theta. That means r theta I, where r is in q of t means k of t with a degree of r less than n. Therefore, this field polynomial can be rewritten as it is product I ranges from 1 to n, t minus r of theta I. But what is theta I? As by the choice, this theta 1, theta 2, etc. theta n are the zeros of the minimal polynomial p over q. So this theta I are the zeros of minimal polynomial over q. Minimal polynomial p, the minimal polynomial p over q. Therefore, the coefficients of this field polynomial alpha t are of the form some h theta 1, theta 2, etc. theta n. But this h of t1, etc. tn, t1, t2, etc. tn are the symmetric polynomials in q of t1, t2, etc. tn. That means the coefficients are in q, means the coefficients are rational numbers. Okay. Yes. Now consider, again come to a definition. The element sigma I alpha, here not that, sigma I alpha. What is sigma I alpha? R of theta I. Why? Because we know that sigma, where alpha equals r theta and sigma I of alpha equals or sigma I of theta equals theta I. Therefore, the element sigma I alpha, where I ranges from 1 to n, these are called the k conjugate. It is called a k conjugate of alpha. Sigma I alpha, where I ranges from 1 to n, are called the k conjugate of alpha. The k conjugate of alpha is denoted as sigma I alpha, and sigma I alpha is defined as it is r of theta I with r falling q of t and degree of r strictly less than n. So this is the definition of k conjugate of alpha. The k conjugate of alpha is denoted as sigma I alpha and is defined as sigma I alpha equals r theta I, where degree of r strictly less than n and r fall in or rt fall in q of t. Okay, r of t fall in q. R is a polynomial with the rational coefficients. Also we know that the field polynomials having rational coefficients. Okay, so by using these notations, that is alpha equals r theta, sigma I of alpha equals r of theta I, sigma I theta equals theta I, and the field polynomial has rational numbers, has rational coefficients, etc. By using, and the field polynomial f alpha t is product I ranges from 1 to n t minus sigma I of alpha. So by using all of these notations and definitions, now let us discuss some theorems, and very important theorems regarding number theory, algebraic number theory. So we will discuss that one in next class. Okay, thank you.